going on in this space. And it had always occurred to me this was very expensive, but apparently it's becoming much more available to everyone now. And I thought I'd talk through just some news about the group. Oakton, this is Oakton, the building we're in. I work for Oakton. Oakton is looking for a couple of resources. If you are a mid to senior level UXer, please contact me. If you're also a mid to senior level front-end developer, I'm looking for someone in that space as well. So feel free to shoot me a line afterwards, or come and see me after the presentation. And regarding next month's talk, we haven't got a speaker lined up at this moment, but I thought I would open the floor up to everyone in our community to do some short talks. We might have 3 or 4 10-minute talks to fill up the session. I'll start advertising that. Please, if you have any little topic or anything you might be interested in presenting on, we'd love to have you present as practice, or to share some experience of yours that you've had in the community. We'd love to hear about it. If you guys in the community doesn't put their hand up, you'll probably get me talking, and no one wants that. Or Donna, I don't want Donna talking, or me. Everyone's heard us talk before. So, and one last thing. There is a discount available to the UX Strategy Workshop with famous Jamie Levy, who's visiting on the 20th of July. If you enter that code, you can get 10% off that workshop if you're interested. But without any further ado, I will hand over to Eduardo. Thank you so much for coming tonight.
Thanks, Monica, and thanks everyone for coming. It's a pleasure to be here. As soon as my presentation is up, scan. That's your PowerPoint. Work. And there you go. So, tonight we're going to talk about eye tracking. And eye tracking is one of those technologies that have come a long way since they first came about. So this is what an eye tracker used to look like back in the 60s, right? So this wasn't even one of the most invasive ones because it used cameras, as you can see here, right? But this was so obtrusive that this was done for reading research, and this was so obtrusive that you had to anesthetize the eyes of your participants with cocaine. Good old days, right? But some of them were really cringy, like with the search coils mounted on a contact lens that you had to put in your eye, and the wire coming out, looking more like a medieval torture device or something out of A Clockwork Orange than something that you'd actually want to use in real life. Nowadays, eye trackers are as cheap as they've ever been. They are robust, accurate, easy to use, easy to set up. This one is the Tobii 4C. You can get one of these for about $200. And when I first started my research on eye tracking, an eye tracker cost something like 50 grand. Right? And some of the professional eye trackers still cost that much, but now the eye tracking manufacturers started marketing these for the general public. So now they sell these for very, very cheap. So I also brought a VR headset there that has built-in eye tracking, if you want to give a go. And that costs around $1,000. So roughly the cost of a regular headset. Some eye trackers even look like a regular pair of Ray-Bans. So they don't even look like eye trackers. In popular culture, eye tracking is often portrayed as part of these dystopian futures, as a way for the government to track your actions, as in Minority Report, or as a way to force you to watch ads, as in Black Mirror. But I personally believe that eye tracking is an incredibly exciting piece of technology with a huge potential to revolutionize how we interact with technology and incorporate attention as a design material for the design user interfaces. So you might have had some. So who has used an eye tracker before in the audience? So a few of you, so you probably ran a study like this, or took part in a study like this for evaluating visual attention in user interfaces. This is not what we're going to be talking about today. Some of you might also be familiar with some applications for eye trackers for interaction, as a means of providing assistive interfaces for disabled users. This is also not what we're going to be talking about today. We're going to be talking, so whereas in assistive interface design, the eyes are meant as a modality to replace the hands, what we're going to talk about is eyes complementing the hands as an additional input modality for interaction design. So my name is Eduardo Veloso. I'm a lecturer in human-computer interaction at the University of Melbourne, and I am a DECRA Fellow from the Australian Research Council. My research topic, in its most general form, is interaction design for emerging technology. So I'm interested in building cool stuff with whatever gadget is out there, right? So I'm privileged to have this opportunity to just spend my days getting my students to build cool stuff. So today's talk is called Building Gaze-Aware Systems, and I'm going to talk about design and implementation of some of the systems that we've been building over the past 5-ish years. This is research that started at Lancaster University in the UK, where I spent 5 years before coming to Melbourne Uni almost 3 years ago. So, the main message that I want to convey today is that designing for gaze is not the same as designing for hands. So the eyes work in a very different way from the hands in terms of how much control we have over it, how much the environment affects eye movements and so on. And I'm going to highlight some of the challenges and opportunities that the eyes present for interaction design in this talk. So on one hand, gaze offers fantastic opportunities, right? So your eyes make some of the fastest movements your body is able to make. Gaze precedes action, so when you're about to do something, your eyes get there first. Gaze is a powerful social signal containing a lot of non-verbal information. Gaze is always there. You can't leave your eyes at home, so it's an input modality that as long as you can track the eyes, you can count on it. And gaze, of course, indicates attention, so it works often as a proxy for attention, though it doesn't tell the full story of attention. And so these are just some of the reasons for trying to use gaze in some kind of attraction technique. But it also presents a bunch of challenges, which I'm going to develop over the course of this talk. So gaze has inherent inaccuracies and imprecision that you must deal with when designing interactions with that. Gaze requires calibration, and this calibration tends to drift over time. And also gaze function, when you're using gaze for interaction, you're asking a lot from your eyes. You're asking your eyes to be a sensor for yourself and an actuator for yourself. And so explain these multiple things. So we're going to talk about some ways through which we can overcome some of these challenges. So let's talk about inaccuracies first, right? So when we're using a mouse or any kind of precise pointer, we can select any pixel on the interface with a lot of precision, right? But not with the eyes. So with the eyes, the precision is more like a region rather than a pixel. And this is partly because of the inaccuracies of the calibration and in the gaze estimation hardware and software, but also because of the nature of human vision. So if you really look at how our vision works, this is what our eyes actually see. So we have this black and white region that is very low definition in our peripheral vision, and we have this small area which is called the fovea that has high def, full HD color vision. So the gray area is good for detecting movement. So imagine that you are in a jungle, you want to be able to catch a sudden movement in your peripheral vision. Whereas in the center of your fovea, you can really see detail. The reason for this is that our retina, the region of our eyes that actually converts light into information, has two types of photoreceptors, the cells that convert light into this type of information. And they're known as rods and cones. So rods are cells that can only see in black and white, and cones are cells that can see in high definition and in color. And they are not evenly distributed in your retina, right? So at the center of a retina, so if you take a line directly from my gaze point, that is this center here, right? So you see there's a lot of cones right in the middle, almost no rods. And in a peripheral vision, you have a lot of rods, very few cones, right? So this creates this small region that's roughly the size of a thumb at arm's length. I promised my partner that I wouldn't make the joke that these guys are there, they're seen from pupil fiction. All right, yeah, you can laugh, come on. And the problem with this is that this is a cone, right, that's coming out of your eyes. And the further you are from your eyes, the larger is the region that your eyes are corresponding to. Right? You might also have noticed that there is this region here where there are no photoreceptors. And that's where your eyes connect to your brain. This region here. So that gives a blind spot in your vision. And you might not have ever noticed this, but I can show you how this works. So if you follow me, do this, and close your left eye, and with your right eye, look at your left finger, right? And wiggle your right finger, and in your peripheral vision, you will see your right finger disappear. Can everybody see it? So that is the light from your from your right finger going directly into your blind spot. So our brain is always fooling us. It's always making these adjustments and filling in the gaps for you. Because we have this small high definition vision, only a tiny area, it means that to be able to paint a full picture of what's in front of us, our eyes need to be jumping around all the time. And most of the time, our eyes are engaged in two movements, fixations and saccades. So fixations are when they stop, saccades are when they jump. And these saccades are very fast. So this is, if you're a bit too queasy about eyes, you might want to look away. But so these saccades are very, very fast movements. They are the fastest movements that our bodies are able to make. And the cool thing about it is that during a saccade, you are temporarily blind. So because if you're, just think about it, right? So if your eyes are making these really fast movements, and your brain was taking in that information, all it would see was just a blur. Right? So our brains are smart enough to shut off and wait for the eyes to stop and then let the information in again. And you can see the extent to which we are blind in this video.
And what Tim shows me next is really surprising. Every time our eyes saccade or make those little jumps, our vision actually briefly shuts down. That means Tim can make things disappear without me noticing.
Now, when he detects a change, I want you to press the space bar again.
Okay?
Okay?
I'm ready.
You ready?
Yeah.
Let's go.
Just look all around the scene, fellas.
You can see the top of the block of flats disappear, but I can't.
You haven't noticed any changes?
No. There's a sort of change. The woman is there.
Tim's computer is tracking my eye movements, and it only makes a change when I'm effectively blind, because my eyes are moving from one part of the picture to another. That's why you can see the changes, but I can't.
How many changes can you solve?
3.
Well, let's have a look. So this is what the scene looked like at the end.
Yeah.
And this, the tower block disappeared, the man appeared, the man and the little boy turned into a woman.
That was it.
So there's maybe 3 changes. But did you notice the bus disappeared?
No. I did not notice the bus disappear.
Did you notice the barriers changed colour?
Not even remotely.
Did you notice the bike disappeared?
No.
Or the branch?
No.
Or the top of this tower?
No. Come on, grab it.
Well, yeah, so this means that, and because we're always making these movements, we are effectively blind for between 3 to 5 hours every week. So that's a huge amount of time for being blind. And you can also check this effect when you look at yourself in the mirror. Try to look from your left eye to your right eye, right? You don't see your eye moving. You just see the beginning and end. But if you look at someone else doing it, you can see their eyes clearly going left and right. Okay, so let's go back. So I just wanted to show these cool things about how your brain is always fooling us. But let's go back to the discussion of inaccuracy. So if our eyes are always trying to fool us and they're jumping around and they're imprecise, why bother, right? And that's a consequence of this mentality that intuitively we always we have this mental model of pointing, right, that is natural to us, right? And we always try, so especially the early work on eye tracking was trying to replace the mouse with the eyes. And that doesn't work because of these inaccuracies, right? So instead of trying to use the eyes as a replacement for the hands, use the eyes to help the hands. Right? So an example of this is work by my colleague Ken Pfeiffer. This was work done in the UK, and he built a series of interaction techniques that combine gaze and touch-based interaction. So the basic idea was to relay wherever the touch events on the screen to wherever you're looking at. So the idea is that you can do this coarse positioning with gaze and the precise positioning with the hands. So you can kind of see how the interaction works like this, right? So in gray you can see where he's looking at, and you can see that the touch events are being just relayed to that area. So even if the gaze is jittery and moving around, the touch is still stable because the precise positioning is being done with the hands. And the cool thing about this is that you can use this combination between where you're looking and where you're touching to create new types of interactions. So you can give different meanings to when the gaze point matches the touch point, and a different meaning to when the gaze point doesn't match the touch point. So, for example, in the next application I'm going to show you, see that when you're looking at the area that you're touching, his application makes a drawing. When the gaze point doesn't match the touch point, you perform interface manipulations and menu selection and things like that, right? So imagine like a little Photoshop type of application like this, right? So you see that when the gaze point matches, it draws, and then it just looks at the color palette up there and touch down to make a selection. So you see that, and the point here is that the circle is only being displayed for the sake of the video, but this could be a completely seamless interaction. You don't have to display anything because the precise position of the gaze point doesn't matter. What matters is the relationship between whether you're looking at where you're touching or not. And you can start thinking about designing for accuracy, because you know that when you are looking at where you're touching, you have precise positioning, but when you're not looking at where you're touching, your hand becomes less precise. So you can use that as to, for example, modulate the precision required to trigger an event, or disable safety critical features in your interface if you know that the user is not looking in that area. When you bring pen and stylus type of interaction into the mix, you even increase your repertoire of interaction techniques even further. So now you have this direct pen interaction and indirect pen interaction depending on whether you're looking at where you are touching the pen or not. So you have this combination, so direct gaze, direct pen, indirect pen. Right? And you can combine these into a bunch of interaction techniques. So here is just an extension of that idea, of the previous idea, but now with the pen, so you can have really precise interaction. So notice how the position, only the coarse positioning is done with the gaze point. The precise position, selecting the swatches, is done with the pen. So you still maintain that precision, but leveraging the speed of the eyes. You can also use to modulate the effect of the pen. So in this case, when the direct pen interaction drops a new anchor point, and indirect pen interaction changes the Bezier handles. So you can see how here he is created this curvature in the tracing of the hand, and you can add new anchors when the gaze matches the touch point. And again, the visualization of the gaze point is completely unnecessary. This is just for the sake of it. So that was the first challenge, right? So gaze is inaccurate, build on that, but gaze is fast. So stop trying to replace the hands and try to leverage the qualities of the gaze and the qualities of the hands. So let's talk about our second challenge, which is calibration. But before we talk about that, let's go back in time. And who invented the aeroplane?
The Wright brothers.
The Wright brothers might say.
One before the Wright brothers.
Who invented the aeroplane?
Santos Dumont.
Santos Dumont. That's exactly right. And there's a Brazilian in the audience. That's right. Anywhere in the world, you're going to ask this question, you're going to get the Wright brothers back. In Brazil, you ask this question, you're going to get this answer back. Every school kid knows. So Santos Dumont was a Brazilian inventor and aviation pioneer who was based in Paris in the early 1900s. And the reason why there is this controversy about who invented the airplane is that even though the Wright brothers flew before him, their plane wasn't self-propelled, his was. Despite his controversy, he was an inspiring pioneer and brilliant inventor, very famous in Brazil. But we're not going to talk about the airplane. We're going to talk about another invention of his. Well, hardly an invention, but something that he was involved in. So going back to 1904, Dumont was still working on the prototype for his airplane. And an important task in the development of these early airplanes was how long it could stay in air, how long it would fly for. And he was complaining to his friend Louis Cartier, the French jeweler, that he felt it was really awkward to pull out his pocket watch to measure how long he could stay in air. Right? It's really awkward. And to help his friend, Cartier went away and soon came back with a prototype of what was the first wristwatch. So Dumont was a bit of a dandy trendsetter in Paris back then, so this soon became like a fashion statement. So over 100 years ago, we abandoned pocket watches in favor of wristwatches, in favor of these interactions at a glance that enabled aviators to quickly measure how long they could stay in air. Fast forward to modern days, we have smartwatches. They're once again locking our hands, asking us to fiddle around with tiny little controls on the screen, effectively shackling both of our hands. Wouldn't it be great if we could go back to that time and have this type of eyes-only interaction with our watches? So if you've ever run an eye tracking study, you're familiar with this. And so this, either a participant, as a participant or as a researcher, you had to put people in front of this, you ask them to look at each of these points in sequence, and then the algorithm detects whether this is a good calibration or not. If it's not, I've got to do it all over again. This might be okay if you have the participant essentially hostage in the lab, but if you're designing interactions, you don't want to have them go through all of this every time they want to use it. And if we're really designing for a smartwatch, we can't even, this is completely unfeasible, right? So the watch is always moving, it's a tiny screen, you know that we've already discussed the problem of forward vision. So remember, it was a thumbs at arm's length, so that's almost the whole size of the watch. So how can we address some of these problems? So to think about this, you need to think about selection from a completely different paradigm from pointing. So if you really need absolute coordinates on the screen to make a selection, then there's no way out. You've got to have calibration. Until someone develops an eye tracker that doesn't require any calibration, you're going to have to calibrate the eye tracker. But if you don't need absolute coordinates, but only relative movement, you don't need any calibration. Right? So that's the key idea here. I mentioned that most of the time we are alternating between fixation and saccades. That is true, except if we are following a moving target. That's the only situation where our eyes make smooth movements. Just try to make a circle with your eyes. Just force yourself to make a circle. You just can't. At best, you're going to do with a lot of polygon with a lot of sides. But if you follow your finger, then you can do a circle. And that's the key idea here, to eliminate false positives as well, and throw away calibration. So imagine that you have an uncalibrated eye tracker, and this is what the eye tracker is outputting, right? A jittery value right in the middle of these. How can you know which target the user is looking at? You just can't, right? Because the calibration information doesn't tell you anything. Now, if the eye tracker is still uncalibrated, but the targets are moving, and your eyes are all of a sudden making these movements, then it's pretty obvious which one the user is following. And that's the key idea here. So if you want to get around calibration, you can just use movement. And I'm going to show you some techniques for smartwatch interactions that build on this principle that we developed a couple days ago. So the key thing here is that the movements must be different from each other. Right? So they can look the same. In this case, they're all circles, but there are different offsets from each other. So all you have to do is look at a certain window and compare the movement of the eyes with the movement of the targets, and you can figure out which one the user is following. And once you have movement, you can use the movement parameters as an interface design parameter. So you can use direction, you can use speed, you can use the radius. Because movement has meaning. And we did experiments where we put a lot of targets on the interface to see if people could still follow them, and they can. This is evolutionary. We evolved to be able to tell things apart with their movement, because that's very important for hunting. So again, color, movement, radius. So in this case, the radius signifies the number of notifications that the app was giving you. And you can do this multi-step interaction to make best use of the real estate of the interface that you don't have a lot of on the smartwatch. Right? So you can have small, tiny movements, small, tiny circles, and then they grow as you follow them. If you keep following them, you can trigger them. You can bring up the application. So these prototypes were built with a wearable eye tracker, but there's been labs working on miniaturizing eye trackers so that they can fit inside your watch. But you can also imagine how this could be built into a pair of smart glasses, for example, or any kind of... all it matters is that you have the eye tracking information. Now, as long as you have that data, you don't need any calibration. You can also use this for interaction with the public displays, right? So same principle, you have a bunch of different movements, you compare the movement of the eyes with the movement of the targets, and you can build public display, interactive public displays like this, where you don't even notice that the person is interacting with the display. All they have to do is follow the moving target. And because our eyes are naturally drawn to movement, you create this kind of interest-driven interaction, where if your eyes go directly to some kind of album in that interface with a bunch of the albums, the corresponding song would start playing, and you can build games around this, and so on. But because we don't need calibration for this to work, we can use this to figure out where the user was looking at. We can use this information to then do the calibration. So I'm going to show you some some here. So in this application, what's happening here, let me play the video again. What's happening here is that this is an installation for a museum. So you approach the display, you're going to see these shooting stars, right, moving around. As soon as the user starts following them, because our eyes are naturally drawn to movement, in the background, the system is calibrating the eye tracker. And once the eye tracker is calibrated, then you can use this type of interaction that requires absolute positioning. So you can do this multi-step type of thing. And the cool thing about it is that you know whether the user is following the calibration target or not by just comparing the movements, right? Which is something they don't have in this type of point-based calibration. So that was calibration. Let's talk about the final challenge here, which is multiple roles that the eyes play. So as I mentioned, when we're using our eyes for interaction, we are asking a lot of them. Right? We are asking the eyes to be a controller and to be a sensor. So at the same time, as an actuator on the interface and as a sensor for our bodies. And this creates a challenge known as the Midas touch challenge. So you're probably familiar with the Greek myth of the King Midas, who with everything that he would touch would turn to gold, and all was good at the beginning. He was turning everything into gold until he touched his daughter, I think, or wife or something, and then she turned into gold. So the principle here is that if you design an interface where everything that your eyes touch become activated, as the user starts just observing the interface, they are activating everything in the interface. Right? So you need to balance deliberate action with the eyes with visual observation. And that's where this idea of visual attention comes in. Right? So we have this pull and push mechanism in our brains, which is often framed as top-down attention and bottom-up attention. So the principle here is that you have deliberate control of your eyes to a certain extent, right? So if you put into your head that you're going to look over there, you can look over there. But if a loud bang happens on your left, your eyes are going to jump there. So we are always balancing this top-down, task-driven eye movements with these bottom-up, stimulus-driven eye movements. Right? So this is always a balancing act. We're going back and forth between these two. Sometimes task-driven eye movements override these stimulus-driven eye movements. Sometimes stimulus-driven eye movements override the task-driven eye movements. So we have some control over it, but not a lot, and it's very difficult. And this next video will show how difficult it is. This is a phone that had some eye tracking capabilities, very limited. It's just knowing whether you're looking at it or not. So you got the idea there. So our eyes, when we're designing for gaze-based interaction, we wish that our users would have complete control over where they're looking, but they simply don't. And this creates a challenge, and you can use this challenge to create playful types of interaction. So you remember 2015, right? Not too long ago. And if I remember correctly, it went a bit like this.
I got it working! My dad taught me about these.
It's well good.
How do you play this thing?
I'll show you, kid. I'm a crack shot at this.
You have to use your hands? That's like a baby's toy.
Like a baby's toy. You have to use your hands. That's like a baby's toy. And that's very interesting because even though, Back to the Future, of course, was very wrong in many ways, they did get one thing right, because 2015 was when Toby released the first affordable eye tracker that would indeed allow us to play these games without using our hands and stop these baby toys that they're talking about there. So I've done quite a bit of research on what I call eye play, which is this idea of playing with using eye tracking as a way of creating these playful experiences in games. And gaming has been a main driver for eye tracking applications. So these are just some. So if you go to this link, you're going to see the wide range of games that have some kind of gaze-based game mechanic in them, and all of these are AAA games. These are like massive $1 million types of games, but they still use eye tracking in a complementary modality. So there's still you can still play the game without eye tracking. So there's nothing core to the game about using eye tracking, but baby steps, right? But it took us a while to get to this reality, right? So before eye trackers were commercially available, a lot of these games came from research labs, meaning there were psychologists and UX designers building games. So you can imagine how good these games were, right? And a lot of research around it was around completion time and error rate, and these let's point and shoot and measure how accurate they are, which they try to get these metrics from UX and HCI and pour them into games, and it just doesn't work, right? So the whole point of measuring performance in these scenarios is just ludicrous. And there was this hidden assumption that, okay, if it is unnatural, it's not fun, so let's make it very natural to make it more fun, right? But this is, of course, nonsense. You know that there's a bunch of games that the control, mastering the control is part of the fun, like walk. You've probably seen this one, they have to make someone walk, but it's very difficult because you can only control the thighs and the calves, which is and there's also this other indie game called There Is Only One Level, and at every level they mess up the control, so right is left and left is right. You know, part of the challenge is mastering the controls. On the other end of the scale, you have this one. So these were researchers back in the day that built this breakout clone, and the idea was that the gaze point was controlling where the paddle was, and so all you had to do to play the game was just follow the ball. And it's funny to read in the paper that they were interviewing their participants afterwards, and one of them was like, okay, when does the game actually start? And that was one of the best players. So, you know, there is this idea that making it natural to make it fun is completely wrong. And to explore some of these concepts, back in the UK, I got some master students that were visiting us and said, all right, let's build something fun. Let's just build an arcade machine and put every sensor that we can put in there, right? So you had this arcade machine with a top-down Kinect that would measure hand gestures. You had another Kinect at the bottom that would measure your feet so that you could walk in place. You had traditional arcade controls, but you had an eye tracker here, you had a touch screen. So I just wanted to create a platform for building these gaze-enabled games and explore new modalities. And you know, the early prototypes looked something like this, where you have these kind of hand control in the arcade, and you could look at enemies and throw fireballs, and that's all fun, but that's still using this pointing and shooting paradigm that we're used to, right? But then things started to get more fun, right? So this was a game that was a touchscreen game, and the idea was they had this bloodstream, and some viruses would start to appear. And to kill a virus, all you had to do was touch it. But if you looked at it, you would multiply. So you had to play with your peripheral vision as you were playing the game. Another game that was a bit more polished was called Shinosaurs, and the idea here is that the players must drag. So this was a mouse point-and-click game. So the idea is that you had to drag these cuties into the pen here, while these dinosaurs were trying to steal them. But if you looked at the dinosaur would get shy, and if you kept staring at the dinosaur would run away. That's why it's Shinosaurs, right? So the player must balance the trade-off between using gaze as an actuator to scare off the dinosaurs, and as a sensor to figure out where the cuties are, so you can actually click on them and bring them into the pen, balancing this idea of using gaze as a sensor and as an actuator. But also, besides control and observation, gaze also plays another role, which is the role of a nonverbal signal. So it tells a lot about how we interact with each other as humans. Just compare the difference between the shy glances of a couple in their first date, to the deep staring of the couple in love, to the distant staring after a fight. Right? So gaze is a very, very powerful social signal. And a colleague of mine, Melody Vidal, built this game that was called the Royal Corgi. And the goal of the game was, so you were in a queen's court, and you wanted to become the Royal Corgi trainer. And you had to convince the different members of the court that you were the right person for the job. But the thing was that each character in the game reacted differently depending on on your visual behavior. So, for example, there was a character that had his wife next to him. And if you stared at his wife's boobs, he would get really pissed off at you. There was another one that was very confident and wanted to get into a staring competition with you, and if you lost, he wouldn't give you his recommendation. And one of these characters was actually voiced by a famous voice actor. I'm going to show you. Let's see if you can figure out who it is.
Good morning. The closest soldier to the king is his most loyal and last defender. He should be fearless, ferocious and fierce. A true soldier that should be taught by a cunning war master. Am I not interesting enough for you? You lack discipline, and respect.
So he detected that you were not paying attention to him and he got pissed off. Anybody figure out who the actor is? That's just me. It was funny that someone told me that after I gave this talk the other day, I made the same lame joke, and someone was saying like, the person next to them came up to them and said, "I'm pretty sure that's Ringo Starr." Another idea of using gaze as a nonverbal signal in games is this idea of gaze awareness, right? So when we're playing co-located games, we're always monitoring each other's gaze to figure out their intentions and their possible actions. Just think of a poker player trying to hide their eyes, or a goalkeeper monitoring the shooter's gaze. So we are now running a series of experiments where we display the gaze from one player to the other player. We're using the game Ticket to Ride, the digital version of the game, as a test bed for a lot of these tests. And what we find there is that by displaying the gaze of the opponent, the player can actually figure out their intentions pretty well, with a caveat that the other player doesn't know that the player can see. As soon as you make the other player aware that their opponent can see where they're looking, they start coming up with all of these crazy visual attention patterns, to looking all over the place. Or you know that this game, the goal is to connect different cities, right? So then all of a sudden you see these players looking at a sequence of cities to pretend that they're going to go for that route instead of the other, and so on. And we're also using this as a platform for training artificial intelligences that monitor the gaze point of players. And we found that we almost double our accuracy as compared to an AI that only looks at game actions by incorporating the gaze behavior into the AI model. And the cool thing, the even cooler thing, is that when we put in the data of the person trying to deceive the opponent, the AI can still figure it out. Right. So this can fool humans, but not AI. So my point here was that we need to move away from this idea that natural is not fun and natural is fun. These are more like independent components. So you can create these traditional types of interaction, like that game that I showed you, where sure you can aim with your eyes and shoot, and that's all fun and that's all natural because you want to look at the place that you're shooting. But you can also bring this to an extreme where it's so natural that you remove all the fun from it. On the other end, you can also create these unnatural types of interaction, like in the Shinosaur's game, where you're forced to interact using your peripheral vision, that are actually a lot of fun. But of course, just don't take this too far, because you can still just create terrible mappings for your interaction technique and create a terrible game. The point here is that a lot of the problems that gaze presents for human-computer interaction design are actually game design opportunities that you can leverage to create playful applications. So I wanted to conclude with some pointers on how to build these systems. Right? So, and I'm going to use, I'm going to talk a bit about some of the work that we're doing now, where we're using a lot of these ideas to create not just applications that the user can control using their eyes, but that react implicitly based on their gaze behavior. And our application domain here is in learning, particularly online learning. We have some projects now that are monitoring facial temperature. So my colleague Tillman here is a co-author in a paper with me where we are looking at using facial temperature signals, patterns, to infer cognitive load. Because essentially what happens is when you're thinking harder, blood flows differently across your face, and you can detect that using a thermal camera. So we are picturing this learning laptop where you have built-in eye tracking, you might have built-in thermal camera. Of course, this doesn't exist yet, but that's the cool thing about being in research, right? So we were building this future before we get there. And the idea here is that we're combining visual attention with these measures of cognitive load, because essentially when you're thinking hard, blood flows to your brain, which brings the temperature of your nose down and the temperature of your forehead up. And if you monitor this difference, you can actually get a pretty good estimate of cognitive load. So I'm going to show you some applications that, this was a project from a master student of mine from last year, where he built this jQuery extension that links to the eye tracker and essentially puts the data into the DOM so they can prototype web applications with eye tracking. So here's think of this is just a series of demos to demonstrate the capabilities of the toolkit. But the idea is that so we're now working on incorporating this into a MOOC to build learning experiences around this. So imagine a video that knows whether you're paying attention to the video, right? So here's a simple example. You have a video there. So this is all you need is a Chrome plugin they built. You connect to the eye tracker, and then if you're watching the video is playing. You look away, the video pauses. It's a simple idea, very compelling. And to build something like this using this toolkit is dead easy. So this is all the code that I'm going to show today for those more less development oriented. But the idea is you have a series of events here. In this case, you can pass whatever object here. In the case of the video, is the video frame, and then you have an event eye in, you have another event eye out. You pass a function there. That in this case, when the eye is in, it plays the video. When the eye is out, it pauses the video. Very simple. Half a dozen lines of code. You build something that is almost magical. And you can take this further. Right? So you can create things like automatic scrolling. In this case, he was building this with a button, but you can imagine something that as you're reading the text scrolls down without you having to scroll. And create these kind of children's book magical experiences. So for example, in this case, we have a figure in the book, and here it says, okay, so once I was 6 years old, I saw a magnificent picture in a book called True Stories from Nature about the primeval forest. And then it goes into the next sentence that is highlighted here just for your sake, but in reality it wouldn't be. And it was saying that it was a picture of a boa constrictor in the act of swallowing an animal. And then as the reader as their eyes get to that passage, the image of the little prince becomes the image of the boa constrictor. So here you can see the gaze point there, and when the reader gets to the point about the boa, the picture changes to the boa. So again, eye in, eye out, very simple, very easy to implement types of interaction that can create potentially magical experiences. And you can also augment the text. So especially for English as a second language learners, you can create these hidden widgets so that you as you're reading the text, you fixate on a word and it's like, I don't know what this is. Just look there.
Constrictor.
You can get the definition of a word, or you can look here and it will say the word out loud so you know what it sounds like. So again, very simple interactions. Try to figure out what is setting your readers back and give them assistance.
Constrictor.
So some of you, hopefully, might be thinking, wow, this sounds cool. I also want to do this. So can I join you? Well, you can. So the University of Melbourne has a completely new Masters of Human-Computer Interaction. So it's a 2-year program, 1.5 if you have a development background, so it's a technical degree. If you want to go deep into HCI, into UX, we do a lot of this stuff in our degree. Or perhaps you are more or less coursework driven and more research driven. You might want to do an MPhil, which is a 2-year program, or a PhD, which is a 3-year program. Under my supervision, these are funded programs, so you actually get a stipend. Yes, people pay to build this stuff. That's great. All right, so and I have a bunch of, so these are not brochures about programs, these are brochures about our interaction design lab at the University of Melbourne if you want to find out more about what we do. There's no marketing collateral there, this is just about research. But so the key takeaways of today's talk hopefully were that designing for gaze requires new ways of thinking about input. It's not the same as designing for the mouse or designing for television. You should use gaze in a supporting role to the hands rather than trying to replace the hands. You can use movement to avoid some of the limitations from calibration. And you should really embrace the nature of visual attention rather than fight it, and build up on that and create these playful experiences that leverage this challenge. So that's it for me. So do get in touch if you're interested in the game mechanics that you can build using eye tracking. I wrote a whole catalog of game mechanics that employ gaze in one way or another. So if you get in touch, I can send you the report. If you're interested in eye tracking studies or eye tracking training, we do all of that in our lab. Also, if you're interested in pursuing a degree in UX, human interaction, eye tracking, all years. Thank you very much for coming.
How good is that? I hope you can appreciate, as a user experience professional, just how amazing that is for me to be able to see this new technology come and completely change the way we think about how people are going to interact with systems in the near future. It is mind-blowing. Just even those last demonstrations of simple JavaScript, being able to navigate and move the page around with your eyes, it changes our world as web designers, web developers. And, it's really inspirational.
Thank you.
Thank you very much for your talk. We've got questions for everybody. Here's one.
Are these slides going to be on the meetup or somewhere? Are you going
There's
to
a
post the
video
slides?
camera recording this session. You can watch it on the YouTube channel.
Oh, yeah, that's fine.
Yeah, I can. I don't know who should I send these to, but I can possibly put them in.
Yeah, that'd be great.
Have you done any explorations of near and far sort of vision, like with eye tracking?
Whether you're looking at 3D?
And depth of field, yeah.
Yeah, there's been some work on that. I haven't done it myself, but essentially when you have 3D vision, your eyes converge or diverge. So there are these two. So in theory, if you can measure how closely where they meet, you can gauge the depth of the gaze point. In theory, it works very well. In practice, it doesn't. You can so what I've seen working is, for example, for augmented reality displays, you can tell whether the user is looking at the HUD or through the HUD. So this kind of coarse-grained detection we can do. Precise continuous, we're not quite there. Because these vergence movements are very, very small. Yeah.
Do you think eye tracking's changed since we've taken up more digital devices, or is it basically evolution? It's how it's been since we evolved.
Well, what I've heard was that because and I never double checked this information, is that there was some, particularly with kids, there was some kind of eye muscle problems that kids would have because they wouldn't read enough, and those completely disappeared when smartphones came along, because people are always reading the whole day. So this kind of, our eye muscles at least are very well trained nowadays. But the eye tracking itself, not really. I mean, from the technology perspective, it hasn't changed much, even from those early ones, right? So an eye tracker is just an infrared camera and some LEDs. That's it. So you get some infrared LEDs that are shining a light into your eye, and that creates a glint that is very bright. And what's happening there is that the computer vision algorithm is looking for the pupil, so this big black spot, and the glint, this really bright white spot. And the pupil moves around, the glint stays where they are. And then all you have to do is compute the displacement. And then, of course, there's a lot of algorithmic complexity behind and 3D models, but I get to stand here and say that it's very easy because I don't have to do this. I just use it.
I think we add to that,
Oh, yeah, sure.
as well as like an issue with kids and VR headsets as well. Because you've got to be careful with kids like let's say 5 years old, because they're what's called a virtual accommodation. Sort of for young kids.
Yeah.
Yeah, just a question on the web demo you had. I noticed you had like a browser plugin. Do you know if there's any plans to have like a native web API kind of built in?
So there are already things that, so if you want to work with, so the problem with that is that you require an eye tracker, right? And because the eye tracker is plugged into your computer, the browser doesn't have access to that unless you install the plugin. But there are, there is one, I think it's called WebGazer, that you can give it a go. And this is webcam-based eye tracking. So it doesn't work nearly as well as an infrared eye tracker because it's just using RGB data. There's even a Melbourne-based company called X Labs that also offer this as a product. So the idea is that you could crowdsource eye tracking studies because anyone with a webcam could use it. And then you have the gaze data directly in the dome, and you can track it. So that all of those problems of accuracy that I was talking about, that's assuming perfect eye tracking. This is far from perfect. Yeah.
What about depth? 3D.
Yeah, that's what we were talking about. So you can get kind of coarse kind of positioning. So you can kind of get whether you're looking here really close or really far. But the divergence movements are really, really small. So it's very difficult to gauge depth.
How far off do you reckon it is from the webcam-based eye tracking being as good as or close to that?
You've got to also think about what you need from the eye tracking, right? So I've seen some very successful deep learning models that can, particularly for cars, to detect where your attention is. So are you looking ahead, are you looking there, are you looking down, And if it is about these discrete regions, it's red. If it is about precise XY positioning, because keep also in mind that our eye movements are very, very fast. An RGB camera will be at most 30 hertz. This one is 90. We used to have one in the lab that was 300. So it all depends on what you want to do with that data. So rather than trying to, all right, when are we ever going to get XY precise position? Maybe think about, okay, what can I do with what's out there now, and how can I build something cool out of this? Because with the simplest information that the eye tracking can give you, you can build a lot of stuff.
Given the example of the Photoshop type experience where you're looking and changing colours and things like that, there's probably a few people in the audience that work with those tools. How long do you think it would take someone to learn to use that new interaction model?
I mean, in the user studies that our group ran, it was grab and go. It was literally because it's all driven by attention. So it's very natural. It just feels right. And that's very difficult to write a research paper where that's the insight. It just feels.
It looked easy.
Because it is.
Yeah, it looked really easy.
So then it can't be far off before all the Macs have this built into it.
Yeah, maybe. My friend would be rich. Not really. They're terrible at patenting things.
So people who are vision impaired or anything, what application does it have?
I mean, as with any novel input modality, it solves some accessibility problems, it creates completely new ones. Right? For visually impaired users, this is a big problem. So I have, it doesn't even work for everyone. Right? So even non-visually impaired people, there are some cases where it just doesn't work. For example, if you're wearing a lot of mascara, now remember the eye tracker is looking for a big black circle. If you have a bunch of mascara there, everything becomes a circle, right? So it just introduces new problems as well. That's probably as far as I can go with that. I think there was another question.
I think just to add to Warwick's point, there is in Android, especially with Samsung, there's something where you can have a feature where if you're looking at your phone will never turn off, like screen won't turn off. Plus, I think they have.
Yeah, that phone that the challenge there of looking at the phone was that was the first phone that had this feature.
Yeah, I think, and the other thing is when I think as you look down, the page goes up when you're reading as well.
Right.
So,
and at this level of granularity of just, are you looking at the upper half or the lower half?
Yeah.
With a webcam, you can do
Pupils dilate depending on what you're looking at. Does that affect the accuracy of the tracking software?
Not the accuracy of the eye tracking software, it only gives you extra information. And so, particularly for these applications of implicit interaction using gaze, we are collecting that data too, because that's a measure of arousal and cognitive load. The problem is that it correlates with a bunch of stuff. So it correlates with emotion, correlates with cognition, correlates with lighting. You've changed the color scheme of the interface. Changed. It correlates with a bunch of stuff. So it's very difficult to analyze this type of data.
Now, I just wanted to add with those X Labs guys from Melbourne. I think we had them here like 2 years ago or something. So Ice Decide, I think, is the software they've got. And so, just to add to your point of that a webcam can already help you with more rough indications. So they offer eye tracking for usability testing of your website. So eye tracking of websites through like purely webcam based. So you don't need no hardware. It's just through the camera.
Yeah, and that's the power of webcam.
So that's already out there for
and it's all free. You can try it when you get home. It's all very easy to set up. But if you've ever used one of these, you will see the differences start. I have a demo there if you have time. I don't know if you do with the VR headset with eye tracking. You can also try it. That's also on the cheap side. As we're discussing, right? So I've used the Tobii one. That costs 15 grand. That's beautiful. This one costs $1,000. It's for the price. It's pretty cheap. It's not as good as the Tobii one.
So good. Thank you very much.